Welcome to Theory of Computation. This is lecture number 14. We have been studying the concept of reducibility. We've also been looking at decidable problems and undecidable problems. Roughly, a problem A or a language A is reducible to a language B if I can use the solution for B to obtain a solution for A. More formally, if I can find a function f going from sigma star to sigma star which is computable such that if x is in A, then if and only if f of x is in B, then I would say that A is mapping reducible to B. Mapping reducibility is only one kind of reducibility, and it is the only reducibility that we have been studying. Using mapping reducibility, we've been able to show that a lot of problems are undecidable. We have a very simple theorem which says that if A is reducible to B and if B is decidable, then A is also decidable. This means that if I want to show that a language is decidable, all I have to do is to reduce it to some already known decidable language. On the other hand, I can use this theorem in the counterpositive form, which means that if I have a language which I wish to show is undecidable, what I have to do is take a language that is known to be undecidable and reduce it to my language. So, if I want to show that A is undecidable, then I would take an already known undecidable language, say U, and show that U is mapping reducible to A. What this does is, it allows us to come up with several examples of undecidable languages without having to actually go through complicated proofs that these languages are undecidable. All we have to do is to show a simple reducibility. Remember, the original proof of Turing, which said that the acceptance problem for Turing machines or the halting problem, ATM, is undecidable. That was an ingenious argument. It was very cleverly crafted and it was a very deep observation. Once Turing proved that, we have one undecidable question that we know of. And now what we can do is take other problems, and if we can reduce ATM to those problems, then we show that those problems are also undecided. We used undecidability, we used reducibility to show that problems are not Turing recognizable also. Once a problem is shown to be undecidable, we can say that its complement is not Turing recognizable, provided we can show that the problem itself is Turing recognizable. Remember that we have a theorem which says that if a language and its complement both are Turing recognizable, then the problem must be decidable. Therefore, if a language is undecidable but it is Turing recognizable, then its complement cannot be Turing recognizable. It's Turing unrecognizable. We also saw that reducibility allows us not only to tell about decidability but also about Turing recognizability of problems. If A is mapping reducible to B and B happens to be Turing recognizable, then A must be Turing recognizable. We can once again use this theorem in its contrapositive form. That is, if A is mapping reducible to B and A is not Turing recognizable, then we can conclude that B is not Turing recognizable. Once again, this gives us a way of showing problems are not Turing recognizable. If we have a question P, which we are wondering whether it is Turing recognizable or not, what we can do is we can try to find a Turing recognizable problem and reduce our problem to it. If we are successful in doing this, we show that our problem is Turing recognizable. On the other hand, suppose we have a question and we suspect that this question is not Turing recognizable, then what we can do is we can take a language that is known to be not Turing recognizable and reduce that language to our problem. Once we find this mapping reducibility, we can say that our problem is not Turing recognizable. We have looked at different problems which are easy are decidable, These are problems for which we can find algorithms or design Turing machines to completely solve the problems. The next level is Turing recognizability. For these problems or these languages, we can find a Turing machine, and this Turing machine accepts exactly the things in the language. However, if you give it an input that is not in the language, the machine may never halt. So in some sense, we can solve this problem in a one-sided sense. We have looked at another example, a very interesting example of a problem called EQTM, and we showed that neither it is Turing recognizable nor its complement is Turing recognizable. So this is an extremely difficult question. This means this problem is very, very difficult. Neither we can find a Turing machine for the problem, nor we can find a Turing machine for its complement. How did we do this? Well, once again, we used reducibility. And what we did was we used some theorems that we have already proved and reducibility to conclude that EQTM is a problem whose complement is not decidable and which itself is not Turing recognizable. Let's have a look at these proofs. Let's recall that EQTM is a collection of all pairs of Turing machines which have the same language. What we did was we showed that ATM is mapping reducible to EQTM. And we did this simply by taking M, W, where M is a machine and W is a string, and constructing two machines. The first machine accepted everything, and the second machine, what it did was it, on input X, it ran M on W. If M accepted W, it accepted its own input. The second Turing machine, M2, ignores its own input. Instead, it runs M on W. If M accepts W, then it accepts its own input. So, it will accept all strings if and only if M accepts W. Therefore, the language of M2 is going to be sigma star if and only if M accepts W. M1 already has the language sigma star because it accepts everything. So, given M, W, we have constructed a pair M1, M2 such that L of M1 is going to be equal to L of M2 if and only if M accepts W. So, if M accepts W, then the pair M, W is an ATM. However, in this case, the pair M1, M2 is in EQTM. On the other hand, if M does not accept W, then the pair M, W is not an ATM. And in this case, the language of M1 is not equal to the language of M2, and therefore, the pair M1, M2 is not in EQTM. So, this is an example of a mapping reducibility. This reducibility shows that ATM is mapping reducible to EQTM. However, this reducibility also shows that the complement of ATM is mapping reducible to the complement of EQTM. Since we know that the complement of ATM is not Turing recognizable, we can conclude that the complement of EQTM is also not Turing recognizable. Well, how do we know that the complement of ATM is not Turing recognizable? We know that ATM is Turing recognizable itself. Well, that is the universal Turing machine which recognizes ATM. On the other hand, we know that ATM is not decidable. Therefore, we conclude that the complement of ATM is not Turing recognizable. However, the complement of ATM is reducible to the complement of EQTM, and therefore the complement of EQTM is also not Turing recognizable. Now, what we want to do is we want to conclude that EQTM itself is also not Turing recognizable. The way we would do that is now we will reduce ATM to the complement of EQTM. If we are successful in doing this, we can follow the same line of reasoning to conclude that EQTM itself is not Turing recognizable. Now we will do is, suppose we take the pair M, W, we construct a new Turing machine which are as follows. M1 is going to be the Turing machine that rejects all inputs. M2 is going to be the following Turing machine. It ignores its own inputs and runs M on W. If M accepts W, then M2 accepts its own input. So what is the language of M1? Well, it's the empty language because it rejects all possible inputs. On the other hand, when will the language of M2 be empty? Well, it will be empty only in the case when M does not accept W. Therefore, if we take the pair M comma W and construct this new pair of Turing machines M1 and M2, the language of M1 is going to be equal to the language of M2 if and only if M does not accept W. What does this mean? If M does not accept W, then the pair M comma W is not in ATM. On the other hand, if M accepts W, then the pair M comma W is in ATM. So if M comma W is not in ATM, that means that would imply that M1 comma M2 is in EQTM. On the other hand, if M comma W is in ATM, which means M accepts W, then the language of M1 is not equal to the language of M2, and therefore M1 comma M2 is not in EQTM. This shows that the complement of ATM is reducible to EQTM. Well, now this also shows that ATM is reducible to the complement of EQTM. So from this we can conclude that EQTM itself is not Turing recognizable, because we have shown that ATM reduces to, the complement of ATM reduces to EQTM. Therefore, EQTM happens to be a language which is neither Turing recognizable nor co-Turing recognizable, which means its complement is also not Turing recognizable. So, EQTM happens to be a language which is extremely general, extremely difficult. You cannot have a Turing machine that recognizes this language or its complement. So it's an extremely bizarre, difficult question. If somebody gives you two Turing machines and asks whether they accept the same language, this question is extremely difficult. Let us now look at reducibility from another point of view. Let's go back to the halting problem. The halting problem is ATM, the set of all pairs M comma W where M accepts W. This problem has an extremely interesting property. The property is all Turing recognizable languages are reducible to ATM. Therefore, this is an extremely general problem. Let's look at a proof of this fact. What we want to prove is that any language that is Turing recognizable is reducible to ATM. Actually, the proof of this theorem is very easy. Let A be any Turing recognizable language. We have to show that A is mapping reducible ATM. So, we're given any arbitrary Turing recognizable language, and what we want to do is show that we can reduce this problem to ATM, and this reduction would be a mapping reduction. Well, how can we approach this problem? This problem seems to be very general. Well, remember that we're saying that every Turing recognizable language is reducible to ATM. We're not saying that every language is mapping reducible to ATM. So, what is the property that Turing recognizable languages have? Of course, Turing recognizable languages are exactly those for which we can find a Turing machine. So, let us take a Turing machine M which accepts the language A. So, since A is Turing recognizable, therefore there exists a Turing machine M which accepts the strings in A, and which does not accept if you give it any input which is not in A. So, let's take a recognizer for A, and now we can use this recognizer to come up with our reduction. So, let M be a TM such that the language of M is equal to A. Note that M exists since A is Turing recognizable. Now, let us consider the following function f given by f of x equals to the pair M comma x. So, this function f, when you give it the input x, all it does is appends M before x, or what it does is it has M hardwired into it, and it takes the description of M, appends x to it, makes the pair, and outputs that. So this function is easily computable. In fact, all it has is a hard-coded description of M and just outputs that pair M comma x. Now, if M accepts x, then x is in A. and if M does not accept X, then X is not in A. So what we have here is a mapping reducibility from A to ATM. This function is computable because we can hardwire M into the program that computes F. Here's a machine F that computes this function. All it does is on input X, it outputs the pair M comma X. Now, X is in A if and only if M comma X is in ATM. Therefore, this function is a reducibility, and we have shown that A is mapping reducible to ATM. This means all problems which are Turing recognizable are mapping reducible to ATM. Let us see what is the consequence of this theorem. Well, remember that we have shown that if A is mapping reducible to B and if B is decidable, then A must be decidable. So, from this theorem we can conclude that if ATM were decidable, then all Turing recognizable problems would be decidable. However, we know that ATM is not decidable. But this theorem seems to indicate that ATM is the most difficult question out of all Turing recognizable questions, in the sense that if it were decidable, then all Turing recognizable languages would be decidable. So, in some sense, ATM is the prime candidate out of all Turing recognizable problems, it is a prime candidate to be an undecidable question. Therefore, it is no wonder that Turing chose to work on this problem and show that this problem is undecidable. Note that by saying that ATM itself is undecidable, we are not saying anything else about all the other Turing recognizable problems. What we know is all problems which are Turing recognizable are reducible to ATM. We know that ATM is undecidable. Therefore, from that we cannot conclude about decidability or undecidability of other Turing recognizable problems. If we are given a problem which is Turing recognizable, it may be decidable, it may not be decidable. However, if we can show that ATM is reducible to that problem, then we can conclude that problem is not decidable. Next topic is going to be recursion theorem. This is a very important theorem in decidability theory, and it's actually very interesting. We have been studying decidability for some time, and the main idea is we first prove that a problem is undecidable, which was ATM, and then we use reducibility to actually come up with a lot of problems which are undecidable. The recursion theorem is a completely different tool, and it can also help us in proving that problems are undecidable. But the basic motivation of recursion theorem is very different. If you think about computer programs or Turing machines, they are mechanical devices which produce descriptions. Turing machines can produce descriptions of other Turing machines. Programs can take input other programs and analyze them. Well, the recursion theorem starts by asking the following very interesting puzzle. Can you write a program that when we run will produce its own description? So, think about this question. I want you to write a program in language of your choice, let's say C++, such that when I run this program will actually print your own program. If you think about it for a moment, this problem is very simple to solve. What you do is you write a program that takes a file and dumps it on the screen. Now, if you run your program and give it the input file itself, it will dump its own description on the screen. However, this was cheating. Now I want you to write a C++ program which when I run will print itself, but this program is not supposed to read anything. So it's not supposed to have any read statements in it, or it cannot read the disk or ask for any input. It should be a program which is self-contained, and when I run this program, the program will print its own description. This is a very interesting puzzle. This puzzle actually comes from mathematician called Kleene who thought about biology, and he was thinking that DNA and biological systems can replicate themselves. So he asked the question whether Turing machines can replicate themselves or whether programs can replicate themselves. Let's try to solve this puzzle. Well, let's try to attempt to write a program that will print itself. So what we will do is I will first attempt to write such a program, and it would not work. And then we will use a very interesting trick to actually solve this puzzle. The first idea would be to start writing a program that prints itself. So you can write main, and then you open your brackets, and now you start printing whatever you have written. So the first thing you will do is put the statement cout less than equals to main and so on, as shown in this diagram. As you can see, this seems to be an unending process. As I write more, I am required to write more. So our first attempt at writing a program that prints itself was a failure. It seems like whatever we have written already, we have to write a statement to write whatever we write next, and this seems to be an unending process. So such a program, if we were to sit down and write it, would never end, and this seems like a lost cause. So can one actually write a program which prints itself? Well, this simple naive way of writing it does not work. If you think about this puzzle, this is an extremely interesting puzzle, and the solution to this puzzle is not trivial at all. Well, the recursion theorem says that this puzzle can be solved. So the first version of the recursion theorem that we are going to study simply says that there exists a program which, when you run, prints itself. Let's look at such a program. If you really want to find such a program, all you have to do is go on to Google and type a program that prints itself, and you'll get several hits, several programs which you can download off the net, and you can run them and see that they actually print a copy of themselves. If you look at these programs, you would not understand much of what is going on. So what I want to do is solve this puzzle of writing a program that prints itself and explain to you the principle behind it. Let's first solve this puzzle not in a programming language but in English. Let's look at the following instruction. Print the following sentence twice, second time in quotes. And what's written in quotes is to be or not to be, that is the question. So if you were to follow this instruction, what would you do? What would you write? You would write to be or not to be, that is the question, followed by in quotes, to be or not to be, that is the question. Let's change this instruction a little bit. Print the following sentence twice, second time in quotes, and in quotes it's written, hello, how are you? So if you were to follow this instruction, what would you write? You would write, hello, how are you? And the second sentence you would write is, hello, how are you, in quotes. Now, let's say that I change the instruction and it looks as follows. Print the following sentence twice, second time in quotes. And in quotes it says, print the following sentence twice, second time in quotes. This is a very strange instruction. What is in the quotes is precisely what the instruction is. Now, if we were to follow this instruction, what would we print? Well, we will print the following sentence twice, second time in quotes, and in quotes we will write print the following sentence twice, second time in quotes. Well, let's see if we followed the instruction, what would be the outcome? The outcome would be print the following sentence twice, second time in quotes, and in quotes print the following sentence twice, second time in quotes. As you can see, if we follow the instruction, we produce the same instruction again. So that seems a very interesting phenomena. Here is an instruction which anyone who follows ends up replicating the instruction. So if somebody were to take a piece of paper, read this instruction and follow it, they'll write down the same instruction again on another piece of paper. So in some sense, this is a self-replicating instruction. Well, programs are nothing but fragments of code which are instructions. So now what we have to do is translate this idea into a programming language. Translating this idea into a programming language is not that easy, but we will do it. The basic idea is we are going to write two small functions. The first function A will print B, and there will be another function B that will end up printing A. And if we run these two functions one after another, then we'll end up printing, the program will end up printing itself. Let's have a close look at this solution. So what we're going to do is start with something simple and work towards the solution. Here you have a program which is in two functions that I have written here. The first function is A and the second function is B. The first function A is very simple. All it does is it assigns X to the string hello and then prints out X, and then after that calls B. The function B does the following thing. It tries to print A. So the function A just assigns X to a string hello, prints that string, and then calls the function B. The function B is going to try to print the function A, but in a very tricky way. Let's have a look. The function B gets X as a parameter, and then it prints A, and then after that it prints X is equal to, and then it prints X. However, you would notice that the function is doing something very strange. It is using the parameter X that it had in order to print X. It's not printing X in quotes, so it's not printing hello in quotes. Since hello came to it as a parameter, it prints X, which prints actually hello on the screen. Let's go further and see this function B. After printing X, it just says cout, and then it prints cout less than X, which means it is actually printing the function B, and then after that it prints B of X, and then it prints the last brace. So this function B is printing the function A in a very strange way. It's not using all of A, all the code of A. It's taking part of the code of A as coming to it from a parameter. Let's run this program and see what will be printed. So if we run this program, what will be printed on the screen? Well, the function A is not going to print anything except hello, and the function B ends up printing the function A. So what will be printed on the screen is hello followed by the description of the function A. Now let's go and change this program a little bit. Let's change this string hello to goodbye. Then what would happen? Well, if I run this program, what will happen is this would print goodbye followed by the function A. You would notice that if I make any changes to this string, I don't have to change the function B. It still prints the description of A. Every time B runs, it ends up printing A. And I can change the string X equals hello to anything I want, and B still works correctly. So how can I use this program to actually write a program that would print itself? Well, suppose now I assign X equals whatever is written in B. So I take the function which is B, I copy that into the string hello. Instead of the string hello, I have all of B. Then when I run this program, what would this program do? This program will first print B and then print A. But that's the program itself. That's exactly the program itself. And so I will obtain a program that when I run, print itself. Notice that this program does not read anything from the disk or does not take any input. So here we have an example of a program that prints itself. What use could such a program be? Well, this program is just a curiosity. It was a challenge. We were supposed to write a program that when we run will print itself. But we will use these ideas to come up with very interesting theorem which will allow us to do a lot of undecidability theory. But let's think about this program a little more. This program, we used a trick that the function A was calling B, and B was printing A not by copying all of A, but by using the parameter which was passed to it. So that was the basic idea. Self-replicating programs are extremely rare. People usually who are programming do not write self-replicating programs. You must have heard of computer viruses. Computer viruses are usually self-replicating programs. However, that's a very negative application of this idea, and people who write computer viruses should actually spend time doing more constructive things. This course is not about programming. This course is about Turing machines. So what we want to do is whatever we have learned from this exercise by solving this puzzle, we want to put that in the language of Turing machines. So what would this puzzle be in the language of Turing machines? Well, in the language of Turing machines, what we want to do is we want to come up with a Turing machine which, when we run, prints its own description. So is there a Turing machine M such that when I run M, it prints its own description? The answer to this question is, of course, yes, since we have already seen that there are programs that when we run, print their own description. Therefore, we should be able to translate these ideas into the language of Turing machines. So how would such a Turing machine look like? What would be the description of a Turing machine that prints itself? Well, we are going to make this Turing machine in two parts. The first part of the Turing machine will not take any input. And let's say we will have two Turing machines, A and B. A will not look at its input, and when we run A, it will print the description of B onto the tape. What B will do is it's going to be a very different Turing machine. It would expect some input. And when it reads its input tape, and let's say that it finds the description of a Turing machine X there, it would construct a new Turing machine which prints X followed by X and output that combination. So the Turing machine A is going to be very easy to make. Let's first look at the following theorem. This theorem says that there is a computable function Q from sigma star to sigma star that does the following. Suppose we give W to this function, then what it does is it prints a description of a Turing machine that prints W. So there exists a function Q going from sigma star to sigma star such that Q of W is equal to P sub W, the description of P sub W, where P sub W is the Turing machine that prints W. Let's try to understand this function carefully. Notice that what we're saying is that when you give a string W to this function, then this function outputs a description of a Turing machine which prints W. So Q is not a function that takes a string W and prints it, but it prints the description of a Turing machine that prints W. One way to think about it is, can you write a program such that when I give it a string X, it outputs a program which when I run will print X. So you are not asked to write a program which takes an input and outputs that input, but outputs a program which, if I were to run, will print X. So this function is extremely easy to write. This function is computable. There is a Turing machine capital Q which computes this function little q. This Turing machine capital Q takes input W and outputs the description of the Turing machine that prints W. Now what we will do is we will describe our Turing machine which prints itself. It will be in two parts. The first part is going to be A and the second part is going to be B. Let's have a look at the part B first. B is going to be a Turing machine that expects some input. Suppose the input to B is a description of a Turing machine X. Then what B does is it finds out what is Q of X. So it finds out the machine that prints the description of X and combines it with X and prints that out. So formally, let's look at how P looks like. So B is equal to, on input, which is a description of a Turing machine X, combine Q of X with X and print the combination. So this Turing machine B is very simple, and what it does is it looks at its input tape and sees what is on there and acts accordingly. Now, the Turing machine A is very simple to make. Let us define A to be Q of the description of B. Now, let's combine A with B, combination here meaning we run A followed by B, and let's see what would be printed on the screen. Well, A is Q of the description of B. So when A is finished running, what would be on the input tape? Well, on the input tape will be the description of B. What would B do? B takes whatever description of a Turing machine it gets on its input tape and computes Q of that and combines it with that description. But Q of B is A. Therefore, it would compute the description of A and follow it by itself, which is B, which is what it found on the tape. So we have constructed a Turing machine which, when we run, prints its own description. This is just a simple curiosity. We started with a puzzle. Can there be a program which, when we run, prints its own listing or its own description or itself? And we found out that the answer was yes. Then we translated this puzzle in the language of Turing machine and said, can there be a program, can there be a Turing machine which, when we run, prints its own description? And once again, the answer to this was yes. And we use the same ideas as writing the program in constructing this Turing machine. We actually translated the ideas from the language of programming languages to Turing machines. What we want to do is now push these ideas a bit further. What we want to do is first prove what is called the recursion theorem. The recursion theorem is not going to be very difficult to prove. We will use the same ideas that we have used in constructing this Turing machine which prints its own description. However, we must first understand what exactly the recursion theorem is saying and how to use it. Once we understand what the recursion theorem is saying, it would be a very powerful tool, and we will use this tool to come up with, to show that many problems are undecidable. A lot of work will go in proving the recursion theorem, but once we have that tool, it would make our life very easy, and we'll be able to show that many problems are undecidable without doing a lot of work. Let's first look at the statement of the recursion theorem. Let T be a Turing machine that computes a function from sigma star cross sigma star to sigma star. So how are we supposed to think about this Turing machine T? It takes two inputs. The first input is description of some Turing machine, and the second input is some data, which is, for the moment, is not going to be very important. And then this Turing machine does something. So you think of T as a function which analyzes a program and some data and behaves in some way. So you can write a function, for example, that takes description of a Turing machine and counts the number of states in it and does something with its data and then produces some output. So T is a Turing machine which is actually analyzing other Turing machines. That's the way to think about it. T is a Turing machine that analyzes some other Turing machines and some data and behaves in some way. Suppose T is a Turing machine like that, or suppose someone writes a program that analyzes programs and does something. Well, then the recursion theorem says the following thing, that there exists a Turing machine capital R such that if we run R on W, then that will behave exactly as if we were to run T on R comma W. What does this mean? This Turing machine R would be as if it's doing the same analysis on itself that T was doing on other Turing machines. So when we run this Turing machine R, it analyzes itself exactly the way T was analyzing other Turing machines. Let's look at formally what it says. It says that if you have a Turing machine T which computes a function from sigma star cross sigma star to sigma star, let's say, then there exists another Turing machine R which computes a function little r such that little r of W is the same as a T of the description of R comma W. So this Turing machine R performs the same analysis on itself as T would have performed on some other Turing machine. The recursion theorem is better understood by saying that we can enhance the power of our programming languages as follows. Any program can call a routine, and what this routine does is it returns the program's description to the program. So a program can actually have access to its own description. This is a powerful thing. So a program having access to its own description means the program can actually analyze itself. This is a very interesting theorem. If you think about it, one can actually write programs that get their own descriptions and analyze themselves. However, programs can only do so much analysis on themselves. So there are limitations to using the recursion theorem. But in principle, you can write a program that gets its own description and does whatever analysis it wants on itself. People who are interested in artificial intelligence find this theorem fascinating because this theorem says that a program can analyze itself. It's a bit like a person who thinks about himself. Many times what we do is we think about how we behave, what we do, what we did yesterday, and we analyze our own behavior and we try to improve ourselves. Well, a program can do the same. A program can actually have access to its own code. It can analyze its own code and it can see how it would behave in some sense, and it can decide what to do after that. So this is a very fascinating theorem. It says that you can have self-analyzing programs. A program can self-analyze itself. This is what the recursion theorem shows us. In terms of programming languages, what we would do is we would say that we have access to the following subroutine, which is we can take a string and assign it to be self. What self means that this string, after this statement is executed, will have the code of the program that we are running. This is how we will interpret the recursion theorem. The recursion theorem says that any program at any point can have access to its own code. How would we prove the recursion theorem? That is the first question. And the second is, how can we use it? Well, the way we prove the recursion theorem is almost identical to the way we wrote a program that printed itself, or the way we describe a Turing machine which, when we run, prints its own description. So let's go through the proof of the recursion theorem first. Suppose T is a Turing machine that's given to us and it computes some function from sigma star cross sigma star to sigma star. We will construct R in two parts again. The first part is going to be A, the second part is going to be B. However, in this case, B is going to be slightly different than it was before. What B will do is it will call T at the end instead of just printing the combination that it was printing before. So let's have a look at it. So the description of B is as follows. B will get two inputs. The first part would be description of some Turing machine X followed by some other input. B is going to completely ignore the other input. The first thing it would do is it will find out what is Q prime of X. Q prime is going to be a function which is very similar to Q of X. It will combine that with the description of X and it would call description of this new Turing machine Z. Now what it will do is write Z, W on its tape and call T. Well, in order for us to describe this whole Turing machine, we have to tell what A is, the original Turing machine, which gets this input and then finally calls B. So the Turing machine A, if it gets an input X, it simply ignores the input, or it moves the input to the right, and before that prints the description of B. And this function is what we are calling Q prime. Once A runs, if we give W as an input to this Turing machine, then what we will have written on the tape after A is finished running is W, the description of B. B looks at its input, it ignores the string, but it looks at the description that it got and then computes Q prime, and thereby it figures out what A is. So it computes the description of A, combines it with its own description, and therefore it's gotten the description of the whole Turing machine. And now it calls T. So we call this Turing machine R. And now it's clear that if we run this Turing machine R on some input W, that would be as if we were running T on the description of R followed by W. So R is the Turing machine that does the self-analysis. So this is a formal proof of the recursion theorem. The way we should think about the recursion theorem is that a Turing machine can have access to its own description, or that a program can have access to its own description. In the next lecture, we will use recursion theorem to prove many problems are undecidable. Once we have done all the work of coming up with a proof of recursion theorem, proving that several problems are undecidable is going to be very easy. I will see you next time. Thank you and goodbye.